Lecture 1.5, Thermal Processes and PV Diagrams. Microsystems, microscopic systems, change due to a working, heating interaction. This causes the state variables to change. In other words, if I have P1, V1, T1, and I call this state 1, and I go through a working and heating interaction, then the state variables will change to P2, V2, T2. And this is now our new state. With this interaction, the state variables must adjust to keep from the ideal gas that P1, V1 divided by T1 is the same as P2, V2 divided by T2 stays a constant. And of course, this is only true for an isolated system where the number of moles are fixed, which is what we normally see. How thermal processes carry this out. And when I say thermal processes, that means we're talking about an isobaric, isochoric, and finally isothermal. Can be visualized with a piston. I see that I spelled visualized incorrectly. So here is a piston by the company Pasco, which is it's a really great piston. So what do we know here? Here's what we know. Where's the gas contained? There's this canister that's then connected inside to the piston. So this is our gas system. Now, the other things that we know here is we know this. You can see here is that note that there is a weight. So we can change this weight. So if we change the weight, that immediately causes a change in pressure. Now, another thing that we can look at is that look at this piston head right here. And this piston head, the piston head moves up and down, and that causes a volume change. And then finally, we can take this canister right here, so we can heat and cool the canister of gas. When we do this, then this changes the temperature of the gas. So you could see that according to the ideal gas law, there's a way to change the pressure, the volume, and the temperature. Now, to simplify this process here, I'm going to draw a piston that looks something like this. So these are the walls of the piston. Now, what contains the gas is this piston head. So let's say that I draw this in this color. That's showing you the piston head. And these are the walls that contain the gas. And then right in here, you're seeing here is that in here is the ideal gas. This guy here is the piston head. And you're seeing that there's no canister. But I'm assuming that the ideal gas in yellow follows exactly what I'm seeing right here. So here we go. So now I got to look at the three processes. So the first process that I'm going to look at is that I'm going to look at an isobaric process, which is a constant pressure process. So that's what we want to look at right there. So let's go look at this guy right here. So what you're finding here is that when a massive pressure, massive piston head, floats in equilibrium, above the gas, F net, the net force on that piston head is 0. Why is it 0? Because it's in equilibrium. Whether it's moving at constant velocity or is at rest, the net force is equal to 0. So that implies here is that the forces must balance. The force of the inside must balance the force of the outside. In this case, we're not worried about forces. We know that the pressure on the inside must equal the pressure on the outside. Now, I just took a picture. I just drew this piston head, so I'm going to steal this piston head again. And I'm going to use this piston head and piston to get a sense of what is it that we're doing right here. So the first thing that I got to do is I got to clean this up a tiny bit. And here's my piston head. So what did I just say here? This is what I said. I said that there's pressure from the outside. And then upwards, there's pressure on the inside. So what that really means here is that there's really 3 different pressures acting on that piston head. So if I look at the piston head, here's what I see. There are 2 pressures pushing down. In other words, this is the pressure of the atmosphere pushing down. And at the same time, there's a pressure due to the piston head. However, there is a equal balanced pressure that has to counteract the atmosphere and the pressure due to the piston head. And that has to be the pressure of the gas. So in other words, what we're really saying is we're saying this, that if I look at the pressure inside versus outside, there's a balance act where this is the pressure of the gas, and over here, that's the pressure of the atmosphere, plus the pressure produced by the piston head. Right? So that is exactly what the pressures are doing right there. So for detail, we know that the pressure of the piston head is then going to equal the weight of the piston head divided, oops, I shouldn't have said weight, I should have said piston head, divided by its area. So isobaric implies that as long as P atmosphere and P of the piston head do not change, the pressure in the gas is constant. That's what we mean by isobaric. So therefore, if I say isobaric, what that tells me here is that then I have P1V1 divided by T1, P2V2, T2. This clearly tells me that the pressure plays no role. So therefore, V1 T1 has to equal V2 T2, and that's our so-called isobaric condition. In other words, when I say I have an isobaric process, the condition is that the ratio of volume to pressure cannot change. So now that we have that, I could then come in and start to interpret what do I mean by an isobaric process. So now let's interpret the meaning of an isobaric process. And you're going to see here is that there's actually two of them. We call this isobaric heating. That means heating from the outside increases the kinetic energy of the gas particles. And then there's isobaric cooling, which means heat from the gas goes outside the piston. So let's look at these one at a time. So here we go. So I'm going to look at isobaric heating. So here we go. From the first law, working plus heating changes the internal energy of the gas. When heat is added, to the gas, It's the adding of heat that increases temperature. But as we've said a couple of times already, this temperature is proportional to the change in microkinetic energy, which then tells us about the change in internal energy. As a consequence, the volume must increase accordingly. So picture-wise, what do I have here? So I've already have the picture of the piston, so let's continue to use that piston picture here. So here's my piston. Okay, so what do I know about this piston here? Here's what I know. So what I'm going to do here is that I know that this piston, that if I'm going to transfer heat into the system, that means I have to have a heat source. So this guy is a heat source. And what that means here is that now heat is being transferred into the gas. So when I look at this guy, this tells me I start off with state 1, which means that I have P1, V1, T1. And now what I'm going to do here is that I'm going to add heat. I'm going to increase the temperature. And as we increase the temperature, here's what I see. The isobaric condition says that if I start off at a small volume and a lower temperature, right? So if I start off at a lower temperature, then I have to have a smaller volume. That's the condition for an isobaric process. So as I add heat, what's going to happen now? Well, what's going to happen is that this is what's going to happen. I now have my piston, and I still have my heat source. It's constantly adding heat to the gas. So I know that it's constantly acting. So as a consequence of this thing here, I start off with a small volume and a low temperature. So according to the ideal condition, this means here that if the volume gets higher, the temperature must be higher. That's what I mean by an isobaric. If I have a higher temperature, then that means I must have a larger volume. So then that means that if I look at my piston head, it then has to get to a larger volume. In other words, the volume in this situation is larger as well as a higher temperature. I should have written 2 and 2. So if I look at this thing, I would say that the pressure plays no role in this because it's being kept constant. So when I look at state 2, the pressure stays the same, but the volume is larger because the temperature is larger. That's what I mean by in isobaric heating. Now let's look at the details. The details is what's going to be important. Okay? The details are important. There's a lot that goes on. Okay? So here we go. So now let's look at the details of the process. So the first thing that you got to do here is that you have to heat energy heat transfer from, maybe I should say this, from the environment. What does that mean? Heat from outside the gas increases K micro. And I should be careful. I should say delta K micro. But now, if I start to look at the details of the gas, what do I see here? The gas collides with the piston head. And when they collide with the piston head, it decreases delta K micro. And as a consequence, the volume increases. So when we say that we have an isobaric process, there's a balance between an increase / decrease of K micro. So the heat increases K micro, but the colliding gas with the piston head decreases it. So what happens? The heat has a continual influx of energy that re-energizes the gas to constantly increase K micro to a higher temperature and therefore a higher volume while keeping pressure constant. So the free body diagram of and Thermo is a PV diagram. So on a PV diagram, it looks like this. So I have my pressure. And my volume. And I'm going to go from state 1 all the way to state 2. And you can see in this process here, it's moving in a straight line because we know that at this point, the pressure of 1 and the pressure of 2 are constant, even though there's working and heating. So this process is an isobaric process. So that means then, I have to add heat energy into this system. So in some sense, it's not the area, but it's to highlight that the process just does move in this way here. So now if I do isochoric cooling, what do I mean by that? So the reverse occurs in isobaric cooling. And what happens in the reverse here is that heat transfers out of the gas. So if I look at this thing, let's stick to our piston here now. So if I look at my piston, here's my piston right here. And what we're going to do here is that we're going to assume that this piston starts off with a higher volume. And of course, I have my contained gas in the canister and then the piston head here. So what we're going to do here is that very similar, the ratio of pressure to temperature must remain constant. So in this case, what we're going to do here is that instead of heat, we're going to put this on ice so that it remains cold. So when I look at this guy, what am I going to see here? Well, I'm going to start off with state 1, which means that I have pressure, volume, and temperature must be high from what we said before. Then what we're going to do here is that we're going to remove heat. In other words, the kinetic energy transfers from the high kinetic energy region to the low kinetic energy region. So what you're seeing here is that the volume and temperature of one are large as the piston head decreases. Now, because this is a floating one, it stays that way. So then if I go and I look at this guy again, here's what I see. I'm seeing that this guy here is actually lower in height now. And so in this situation, if I start off at a state of V1, T1, in other words, this is larger, this guy here is higher, a higher temperature, then the isobaric condition says that these guys must keep the volume and temperature ratio fixed. So therefore, I have to have a smaller volume and a smaller temperature to do that. So in this case here, we're seeing that this guy is going to be smaller, and this guy is going to be a lower temperature. And so what happens here is that, here we go, the gas continues to flow out. And as it does that, the ratio of volume to pressure has to stay constant. And so then if I look at my state 2, then I'm going to have the same pressure, but a smaller volume, smaller temperature. So if I look at the details, it's going to be the same type of thing. But it's a little bit trickier. So if I look at the details of the process, here's what we see. The work of piston increases K micro. And we can see that with the bigger volume, higher temperature. And as a consequence, this decreases the volume. So now what happens here is that heat is transferred from high, and the high in this case is going to be the gas, to a low, and that's going to be the cold reservoir. That decreases K micro. Again, there's this knife edge balance. There has to be a balance between there has to be balance between increase / decrease of K micro. So if I look at this thing, there's this balance again. So then if I go in and I go on a PV diagram, what do we see here? Well, it's going to look something like this. So if I have my state 1 here, and I have my state 2 out here, then the process goes opposite. So what you're doing here, you are removing heat. So if I look at this guy, this is what I'm seeing. No, I don't like this color. I'm going to change this to something else. How about if I change that? Okay, so now we have 2 more processes to go after. 2, isochoric, which is a constant volume process. So if a piston head is locked in position, the volume is constant. From the isochoric condition, we see here that pressure, volume, temperature, pressure, volume, temperature, that if the volume is fixed, then what we see here is that the ratio of pressure to temperature must be constant. And this is the so-called isochoric condition. So what this tells us here is that this condition, it forces the pressure temperature ratio to remain the same, regardless of what happens. So what we're going to do here is that we want to interpret what happens in an isochoric process. And what we find here is that there's 2 processes. There's isochoric heating and isochoric cooling. So let's start with isochoric heating. So what we have to do here is that we have to increase temperature. So to increase temperature, heat must be added. So how do I set this up? So let's draw a piston. So here's our piston. And what we want to do here is that we want to take our piston head and we want to lock it in place to make it isochoric. So again, these are the walls of the piston. And then inside of here is our ideal gas. So when we're looking at this thing here, this guy right here is our locking pin. And what we're going to do here is that we're going to add heat. That's what we mean by isochoric heating. So what should happen here, so if I take this exact same piston, well, let's not do that. How am I going to add heat? Well, I need an external source. So I'm going to have a heat source that then goes something like this. So when I look at the heat, we clearly have heat flowing into the gas. So what do we expect here? So if I look at the isochoric condition, if I start off with a low pressure and a low temperature value, we can clearly see here is that I'm going to have a small pressure and a small temperature. So in other words, because I have a low temperature, I expect that I'm going to have a low microkinetic energy. So therefore, when they're hitting the walls, the pressure is going to be low. But now what happens is that when I heat this up, I expect the pressure to go higher because the temperature has increased. And because the temperature has increased, so now I have a high temperature. And as a consequence, I'm going to have a higher K micro, which then means I'm having more collisions per second. So now what I'm going to do here is I'm going to copy this setup and I'm going to transfer it over to here. And then what I'm going to do here is that I'm going to adjust it now. So what happens when I do that? Well, what happens here is that I know that the pressure has to go higher as well as the temperature. And so that ratio has to be a constant. So let's look at the details just to make sure that we're clear on them. So details of the process. So when I see this, what am I seeing? There's heat from the environment. And remember what I mean by environment again, is that it's not coming from the gas, it's coming outside the gas. So heat from the environment increases temperature, and as a consequence, K micro. So then what you're seeing here is that now that I have a higher K micro, that means that you're going to have a larger impulse. Nope, not a larger. That's not correct. I'm going to have a higher collision rate as well as a larger impulse on the walls, which increases pressure. So then on a PV diagram, what am I going to see? Well, I have a diagram that's going to look like this. This is my pressure, and I'm going to start at a lower pressure. And this is what I'm going to call P1. This is state one, and the volume does not change. So then I'm going to increase to pressure 2 here, which is a higher pressure. So as I move along this thermodynamic path, what I'm doing here is that the way I achieve it is that I add heat. And that's what I mean by isochoric heating. Now, the other process is isochoric cooling. So when I look at isochoric cooling, the reverse process occurs. This means here is that heat from the gas flows out of the system. So this heat is within the system. So heat is removed. And that implies here that there's going to be a decrease in temperature and K micro. That changes the pressure proportionally. So let's set this up. I believe I have an image of the piston still. So let me put this right here. And so what you're going to see here is that now we don't have heat anymore. What we're doing here is that we're now have a cold source. So this is the low kinetic energy region here. So what ends up happening here, let me copy this for the next one. So what ends up happening is this, that in this process, I'm now in a state where I start at a high pressure and a high temperature. And as a consequence, heat is then going to flow out of the gas and into the cold source here. So what does that mean here? So now I have a high pressure and a high temperature. So what I'm seeing here is that in this situation, I have a high temperature, which means I have higher kinetic energy, or how did I write it earlier? Yeah, I have a higher kinetic energy. So therefore, I'm going to have more collisions with the walls. So I get a higher temperature. So now what I'm going to do here is that as heat moves from the gas to the cold source, we're clearly removing heat from the gas. So what we expect here is that the pressure has to do what? It has to decrease. Why did it decrease? Because the temperature decreased. That means the gas now has a low temperature, And as a consequence, it has a low K micro. So the collisions are less, and therefore the pressure is lower. So then I'm going to P2, T2, and again, that's because heat is leaving the system. So this process is very similar to what we just wrote about. So let's just look at the details quickly. So the details of the process. We're seeing here that heat is removed from gas to the cold source. That implies that we have a decrease in temperature and K micro. As a consequence, there's going to be less collisions on the walls of the container, which then tells you that you have to decrease pressure proportionally. Excuse me. On a PV diagram, well, it's going to look exactly with what we drew up here. How about if we copy it and then we just have to slightly modify this graph? So if I look at this graph, here's what it's looking like. So in this case, we switch 1 and 2. So this is 1. So if I come over here, I start off with state 1 and then I go to state 2. The arrow goes in the opposite direction. And what you're seeing here is that we have removed heat. Finally, we're at our last process. This is an isothermal, which is a constant temperature process. Now, an isothermal is very, very similar to an isobaric process. Of course, the parameters are different, but this process has to work essentially on the knife's edge to keep a balance of decrease and increase in microkinetic energies. So here we go. So now what I want to do here is that I got to set you up so you know what we're looking at. So the first thing that we need to do here is that let's look at our piston here. So when you look at the piston, what you're seeing here is that our gas is contained not only in the canister, but also inside the piston. So the way we keep the canister or the gas at a constant temperature, we then do a process. So I imagine that I have a container. And what I'm going to do here is that I'm going to put this gas in a hot water bath, let's say, or it could be a cold water bath, depending on what we're trying to do here. So then here's my canister here. And then you'll see that there's a rubber stopper right at the canister right here. And what we're doing here is that we're putting the gas into the canister. And let's say that in this situation, we're going to say here is that this is a hot water bath. You'll see we'll change this a little bit later into a cold bath. So now I got to set this up into my piston. So you could see that I have hoses. So then I'm going to take my hoses and I'm going to connect it to inside the piston. In other words, I still have my piston right here. And so again, here's my piston walls. And then I have my piston head, which contains the gas. And then the gas is able to flow with both of these guys in here. Now note that this is challenging to draw and keep drawing it like this. So what we want to do here is that we want to simplify the picture. So the way I'm going to represent this picture is that I'm now going to have my piston, as we've talked about before. So instead of drawing the canister and the hose, I'm going to delete them. So what I have here is I have my piston head right here. Inside my piston, and I'm only going to focus on the gas inside. But I know that there's a canister. So now what I'm going to do here is that I have to go in. Let me copy this here for a little bit later. I'm going to copy this. So what I'm going to do now is that I'm going to put in a canister. I'm going to put this whole piston into a hot water bath like this. That's my water bath. And so what happens is that this is what happens. Now heat flows in from all sides. And I'm going to say, that's what I have right there. Okay. So here we go. So now that I'm talking about an isothermal condition, here's what we're seeing. The isothermal condition shows the pressure, volume, product must remain constant. Okay, must remain constant. So again, if I look at my ideal gas laws scenario here, you can see here is that these pressures cancel out and therefore tell us that pressure 1 times volume 1, pressure 2, volume 2, this has to remain constant. This is what I call the isothermal condition. Okay, the isothermal condition. So what we want to do, I'm going to have to copy this. So what we want to do is that we want to go in and look at the physical meaning of this thing. So then so if we want to interpret this process, there are two of them. There's a isothermal heating as well as isothermal cooling. So here we go. So let's start off with isothermal heating. So what happens? In this situation, what we're going to do here is that we're going to decrease pressure while keeping temperature and K micro fixed. So here we decrease pressure and increase volume while keeping temperature and K micro fixed. So I'm going to have to modify my picture, but here's what I'm looking at. So here's my system right here. I'm going to put this right here, and then I'm going to look at this guy again, and here's my pictures. So what I need to do here is that I need to start off at a lower volume. So let's draw that in. So I have a small volume. And I see here is that heat is coming into the gas. So if the pressure and volume are stay constant, then that means that in this situation, the pressure is high, but the volume is small. So I got a large pressure, but my volume is small. So what this tells me here is it does this here. The fact that I have a high pressure, so I have a high pressure, that implies that I'm going to have, of course, more collisions. And because I have more collisions, that volume starts to expand. But the fact is that I have to keep the microkinetic energy constant. So as the gas particles collide with the piston, they decrease in kinetic energy. So that means I have to add heat in order to keep that temperature constant, or K micro. So then this guy is going to expand in such a way that the pressure is smaller because I now have a larger volume. So here you're seeing that I have a lower pressure. Why do I have a lower pressure? Because there's less collisions with the walls. So then we see that the pressure drops and the volume increases as I move to that state. So let's look at the details here. Here I go. So the details of the process goes like this. And I think this is tricky, by the way. So gas particles collide with the piston head. That tells me that they must decrease. There has to be a transfer of momentum. Therefore, the velocity has to be smaller. So K micro decreases. But as a consequence, I should have probably done this slightly different. We should have said this here. So this implies here is that the volume increases while there's a decrease in K micro. But it can't decrease K micro completely. So what you find here is that you have to re-energize the gas particles. So then heat increases K micro by re-energizing them by that influx. So what you're seeing, as you saw with the isobaric process, there's a balance between the decrease. This is the decrease in K micro because they collide with the piston head. And then there's an increase because there's a continuous heat flow so that K micro stays the same to keep the pressure constant. So on a PV diagram, we see here is that pressure times volume is equal to a constant. So this immediately tells me that the pressure is proportional to 1 over the volume. So when I plot this, then I'm seeing this type of curve. I start off at state 1, and this tells me that the pressure is high. And then I'm going to go to state 2, and the way I go to state 2 here is that this follows this 1 over the volume process here. And so what you're seeing here is that this tells me that this is a small volume. This here tells me that this is a high volume at the same time that this is a lower pressure. So what you're seeing here is you're seeing this 1 over volume behavior. And the only way you can do this is if you add heat. This is isothermal heating. Now, if I look at isothermal cooling, it's very similar. So then if I look at isothermal cooling, so what you're seeing here is that in order to increase pressure, while keeping temperature and K micro fixed, the isothermal condition requires volume to decrease. So now I have to modify my piston picture. So let's go look at my piston picture. So it's looking like this here, but now we don't have a heat source. We're talking about cooling. So what that means here is that we have to have a cold water bath instead of a hot water bath. And this one is a little out there. So let me show you what I mean here. So if we have an isothermal process, look what has to happen. There has to be a balance between the decrease and increase in K micro in order to keep the temperature constant. So here we go. Okay. So what's going to happen here is that now, if you look at the curve, I'm starting at a lower pressure and a higher volume. So what you're going to see here is that this piston now is going to start to move down. So now if I have a low pressure, but a large volume, here's what you're going to find here. That this ratio must be like this. That means I have a low pressure, and as a consequence, I'm going to have less collisions. Even though they're moving the same speed, they have to travel farther. That's why there's less collisions with the walls of the container. But now what I'm going to do here is that in order to decrease the volume, I have no choice but to increase the pressure. So if I look at this guy right here, here's what I'm seeing. So it's the work of the piston that increases. So as a consequence, it turns out that we have to remove heat. So in this situation, the heat is flowing from the gas into the cold, right? So it's flowing into the gas, from the gas into the cold. So there's a two-step process that's actually happening. So what's the two-step process? One, the pressure is going to decrease because the volume has decreased, and I screwed up. Let's say that this is my decrease in my volume right here. And again, the piston head is moving down. So what you're seeing here, as the piston head moves down, you're finding then that the pressure here is then has to be a higher pressure. And because it's a higher pressure, I have to have more collisions, even though the speed of the particles are the same. So let's explain this through the details. Details of the process. So first, what do we see here? That the work of the piston decreasing volume increases K micro. So the piston is what's increasing K micro. But in order to keep the temperature constant, heat transfers from the high, which is the gas, to the low, which is the cold source, that decreases K micro. Once again, I have that balance. So the balance between the increasing part, that's the piston head, versus the decreasing part, that's the gas, that's the heat flowing out of the system of K micro, to keep temperature equal to a constant. So then, on a PV diagram, it looks very similar to what we just did right over here. So if I grab this image here, what am I seeing here? So if I look at my PV diagram, now I am going in the opposite direction. That means here that when I'm looking at this thing, these values here are changing. So now, right here, this is state 1, and this is state 2. So you could see here that this is 1, and this is 1, and then this is 2, and this is 2. But this time, it's moving in this direction. So you can see the compression increases the kinetic energy. And on the other hand, we have to remove heat to keep the temperature constant. Now, just to finish off the section, we want to think a little bit about problem solving strategies. And this is right off the web page. And there's some material in here that we haven't covered yet, but I just want to look at this with you. So what you're going to see here is that when I look at this, you want to determine the state of the material by looking at the ideal gas law and the internal energy. It's the internal energy that sets everything. So for the initial state of the gas, there's pressure, volume, temperature, and mole number. But remember what I said about mole number. It's non-existent effectively. Most problems are closed. There are some exceptions, but not that many. And so what you're going to find here is the PV diagram. You have to be able to identify the process and its state variables at the endpoints. Because remember, the internal energy is path independent. It only depends on the endpoints. So once we do this, we look at the process and we say what? Identify the ideal gas law conditions. We will talk about adiabatic in the last process, excuse me, at the end of this chapter. And so we have isothermal, isobaric, isochoric. Now, you got to remember to convert the units. The units are important. The units should be in pascals, they should be in meters cubed, and they should be in Kelvin temperature here. So here's a strategy to try to look at this and then solve your problems. Look at the examples because that's the most important piece to look at.